My name's Regina Nuzzo, and I'm a professor teaching statistics at Gallaudet University in Washington, D.C. And this is my office behind me. So I have a PhD in statistics from Stanford University. And I also, after I finished that, I went to University of California, Santa Cruz to do a graduate program in science writing. So I've been doing both for about 10 years now, teaching statistics and also writing about statistics and probability and science and medicine for a general audience for like LA Times and Reader's Digest and New Scientist and Nature. So I'll be talking a little bit about all of that today. One thing that I should mention, I'm a cyborg. By that I mean that I was born mostly deaf and then my hearing went down over time, and a couple of years ago I got a cochlear implant. So I am a 2-year-old toddler cyborg, and just wanted to mention that so you know where the deaf accent and voice things come from. So what we're going to be talking about today, how not to fool yourself with data analysis, one of my favorite subjects. So let's get started on that. What am I going to be talking about? First, a bit of perspective on where we are and why we're here, and then specific cognitive fallacies that can trip you up, and then specific debiasing techniques that you can put to use. So reproducibility means a lot of different things to a lot of different people, and there are committees that are looking on how to define it, what it means. But for the purposes of what we're doing today, I think that the following taxonomy by Victoria Stodden is kind of helpful. She talks about empirical, computational, statistical. Empirical is the bit that's saying, have you actually recorded enough of your methods and your materials and the protocol of your experiment and written it down and shared that so that other people can reproduce the actual experiment. Pretty simple. The second one is the one that she's interested in, computational, saying that, well, that's not enough. We're working sometimes from databases. We need to put our code up there. The code is very important, so we need to make sure that the computational part of our studies is reproducible. And then finally, statistical, and that's the part that I'm interested in. What are we doing in the data analysis that it's not just about the data and it's not just about the methods? What is it that we're doing during the analysis that could lead to problems and to your results not being reproducible? I want to share a few quotes that I think can really illustrate where we are. Why are we talking about this now and we were not talking about it 50 years ago? Keith Baggerly, a statistician, said that, we're looking at way more variables than we ever did in the past. And we don't have any gut intuition about that. Our gut intuition, he said, sucks. Who can think in 100-dimensional space, but that's what we're doing in the area of big data now. So things have changed in that way. We also have different computational software, and Andrew King at Dartmouth said he calls it the steroids era of social science, and by that he means we have this point-and-click software that can let us just sift through our results until we find the p-value that we want without necessarily understanding the theory or the concepts behind the analysis that we're doing. And he said this is a problem. This is a little bit of a cheat, and it gets you where you perhaps shouldn't be. And Hal Pashler, also on the same theme, said it doesn't matter if you're not using, if everyone else is using, then it still affects you. He pointed out that if people are getting these remarkable results, it raises the bar for everyone else. And once people started reporting brain behavior correlation to 0.85, he said, which is just too high. It has to be a fluke. It wasn't real. But everyone's reporting it because of these steroid methods that Andrew was talking about. And you got a 0.4, then you've got to be saying, well, what am I doing wrong? So the pressure is on you to then use these steroids and get results so you can publish. The big picture perspective on this comes from Saul Perlmutter, astrophysicist at UC Berkeley, who said this is just where we are in the science cycle. science is an ongoing race between inventing ways to fool ourselves and then inventing ways to avoid fooling ourselves. And we're at the place where we have the big data and the software. We're fooling ourselves. Now we just need to find a way to protect ourselves against that. So my part of this came when I wrote a couple of features for Nature that I encourage you to look up. One on p-values and the problems of misinterpreting them, and then how scientists fool themselves. And that's what I'll be talking about today. Here's the handy-dandy infographic that I made to go along with the article in Nature. So very pretty. You can put it up on your lab wall. 4 cognitive fallacies in research, and the 4 debiasing techniques. And that's what we'll be talking about today. So the first one, hypothesis myopia, collecting evidence to support a hypothesis, not looking for evidence against it, and ignoring other explanations. So how does this come up? We forget that we can go forward. If P is true, then we'll observe Q, but that doesn't mean that P is the only thing leading to Q. And I think a good example of this is one that I found when I was talking to an analyst in the intelligence community. And he talked about there was a pharmaceutical factory and in Sudan, and in 1998, CIA analysts got soil samples from outside it, and they found chemical signatures that indicated chemical precursors to nerve gas. And the U.S., this was a key piece of evidence, physical evidence, that the U.S. relied in making a decision to eventually bomb in 1999, to bomb this pharmaceutical factory. And it was only after the fact, when analysts and the scientific community were looking at the data and realizing that no one really pointed out that there were many other things that could have led to this. So if P then Q, if nerve gas was being produced there, then we would expect to see these chemical signatures in the soil. But in their confirmation biased haste, they didn't look at all the ways, or didn't present to policymakers all the different ways that other things might be leading to seeing this chemical signature in the soil. For example, it might be resemble something that's naturally occurring, or maybe there was nerve gas being stored there, but not made there, or all sorts of other alternatives. And when the analysts presented the information up the decision-making chain, they just talked about that straight line up, saying if there's nerve gas, then we would expect to see it here, and we saw it here, therefore probably nerve gas. And they ignored all the alternatives. And it was only afterwards that they really examined the evidence and concluded that it wasn't really as airtight as they had hoped. It wasn't as strong. And the bomb injured 11 people, killed 1 person. And the analyst that I talked to is Steve Belsko at Lawrence Livermore Berkeley Lab in California. And he said that this was likely an example of confirmation bias with, unfortunately, deadly consequences. Another thing is not using likelihoods correctly, and this one gets a little bit more statistical. So the following is a bad way to reason, but this is what we're doing with our statistical machinery. If the null hypothesis is true, then it would be unlikely to observe Y. That's a premise that we're working off of, and we've just observed Y being some data pattern. Then we unfortunately make this wrong conclusion of saying, okay, the null hypothesis is very unlikely, and the alternative must be likely, and this is wrong. So let me give 2 examples, one to show why it makes sense at a gut level, and then another one to show why it doesn't always hold. So the first one, if we're talking about a hypothetical drug for weight loss, and so that's the null hypothesis, is the drug has no effect. And so that first statement would be, well, if the drug has no effect, then it would be unlikely to observe a sample where everyone who got the drug lost weight and everyone who didn't lose weight. Okay, and then we ran our experiment, and that's exactly what we observed. And so we conclude, well, therefore, that null hypothesis is unlikely. We're going to reject it. We're going to accept that alternative hypothesis of the drug having an effect. Okay, so this is what we do every day. But actually, it's not so great, and you can see it in the following example. If I'm talking about playing poker with my friend, my null hypothesis is that he's not cheating. And so if that's true, if he's not cheating at poker, then it would be unlikely to observe him getting a royal flush. But he just had a royal flush, and he just won with that. So according to this method that we use in science, therefore, that null hypothesis is unlikely. It's unlikely that he's not cheating at poker. And the alternative hypothesis, that he is cheating at poker, must be likely. Well, if we do this, then we never have any games of chance, and we never get to bet or play the lottery because there are unlikely outcomes. But that doesn't mean that the opposite must be true. So what's missing in there is talking about the alternative hypothesis. How likely is it to observe our data under that? How likely is the alternative hypothesis? So an example that I think illustrates this, in 1999, Sally Clark in the UK was accused of killing her two young sons. So she had two young children, and they both died, one a few years later than the other. And she was accused of killing them. So what happened in the courtroom, the idea, the null hypothesis, innocent until proven guilty, starting with the idea that Sally Clark did not kill her sons. And so then, according to this process that we're doing, we should then say, but we observed two deaths. So what are the chances of those two deaths being of natural causes, being of sudden infant death syndrome? And you can run through data and different things, and experts can estimate that the chances of having two SIDS deaths in one family is 1 in 297,000. So in most court cases and most reasoning that we do in science, we just stop there. And so we say, okay, the null hypothesis is that she's innocent, but yet the chances of two SIDS death is 1 in 297,000. Well, that's very unlikely. So therefore, that null hypothesis is unlikely, and we have to go ahead and conclude that she's not innocent, that she did kill her kids. What's missing here, and she was convicted and in prison, and then statisticians started to get involved, including the Royal Statistical Society. And they said, but wait a minute, we're not looking at the chances under the alternative. We can't just look at one side. We just can't look at the null. We have to look at both. So what are the chances of having two child murders in one family? And they're able to, again, experts are able to estimate this based on past data and different things. And they've estimated that that was the chances of that happening. You would get only two children being killed within one family, 1 in 2.7 million families. So that's even less likely. So which one are you going to pick? The evidence is actually pointing in favor of her being innocent. The chances of SID death is less unlikely than it is that she killed them. But yet they went ahead and convicted her. So based on this and the other things, they reopened the case, and they actually overturned the conviction, and the court started to look at other situations where parents were accused of killing their children, and they started to overturn some of them. It was too late for Sally Clark, unfortunately. She died of acute alcohol poisoning, so it's a little bit tragic there. But it's the same problems that we're having when we're doing our scientific process. All right, next fallacy, Texas sharpshooter fallacy, one of my favorites. Seizing on random patterns and mistaking them for something interesting. I think it's very visual. Say you've got this Texan who's just banging away at a board at random, and then he grabs his paintbrush and finds the spot with the biggest cluster, and then draws the target around that, and then he steps back and says, I am awesome. So this is kind of what we're doing with our data analysis, unfortunately, and one of the ways it comes through is p-hacking. And you all have probably heard a lot about p-hacking. Researcher degrees of freedom means that we have a lot of freedom, a lot of choices to make in the data analysis process. And we realize that every time we're making a choice that's leading us towards significance, this weakens our p-value. This was illustrated. A journalist, John Bohannon, did a fake chocolate study. Actually, he did it for real. He had, I think, 15 participants, 18 different measurements, weight, cholesterol, sleep quality, etc. Half got the chocolate, half didn't. And then he checked their weight at the end. And since he collected so much data, and since the sample size was small, and that means the results are going to be more variable, he was able to slice and dice and do all these things until he found that yes, chocolate helped weight loss. And he put out a press release, and it got picked up in all these magazines and that sort of thing. But really, he just sliced and diced until he found something, and then cherry picked only the findings that turned out to be true. So I love this example. It's kind of a fun one. So here are a couple of apps that I encourage you to try out and play with. The first one's much more in-depth than the second. The second goes along with a very nice article on science by Christia Schwanden. So I don't think I have time to go through them here, but I'll leave them for you to look through. All right, third fallacy, asymmetric attention. This is where you are checking the unexpected results, but the expected ones get a free pass. What do I mean by that? So you only get the errors that you want. And a great example of this, there was a famous 2010 paper by two Harvard economists, Carmen Reinhart and Ken Rogoff, and they had analyzed data from a lot of different countries since the Second World War. And they found that the mean economic growth fell when the size of a country's debt rose above 90% of its GDP, its gross domestic product. So the idea was that countries should tighten their belt and rein in debt, or else they will just destroy their economy. So it made a big splash all around the world. Lots of people were using it to buttress this idea of austerity. Sounds great, right? But the University of Massachusetts graduate student Thomas Herndon, for part of a class, tried to replicate those results using the data. He tried to work through the math, a very simple thing, and he couldn't get the numbers to work out no matter what he did. And finally, he asked the authors for the data and found something very interesting, and that's why you see Stephen Colbert there, because things did not go well. So he was shocked when he saw that they were using an Excel spreadsheet, and you might be able to see here. This was the mean that they were using down here. So this should be the mean of all the countries stratified by different things. Remember I said 90% or above for the debt ratio. And the average, oh, wait a minute. They did not drag that little window down far enough, and they left out these data points, including a 2.6, which actually pulled the results differently. So one little error. So this was not fraud. I don't think anyone thinks this was fraud, but it does look like this example of this fit in with ideas that the results here fit in with ideas that they'd already been covering and writing books on, and they were very much proponent of this idea of austerity. And so why would they question this? They made this very simple human error that everyone makes, but it was in favor of their hypothesis. So why look? But you can bet if for some reason the one that they left out was something that went against their hypothesis or previous beliefs or gut, then they would have gone through the fine-tooth comb and found this error. So this is a very human problem that happens to a lot of people. And so when you reanalyze this, the average growth dropped from 3.2% to a much more moderate 2.2%, and didn't fit their theory quite as much. You can see, and at the bottom it doesn't quite have the same thing going on. And it was so famous that Thomas Herndon got to be on the Colbert Report talking about this. So that is a lesson. You do not want to be on the Colbert Report because of your asymmetric attention. Next one, just as storytelling. This is where you find stories after the fact to rationalize whatever the result turned out to be. And this is just so after Rudyard Kipling, who wrote those just so stories about how the elephant has a long trunk. And he wrote these highly, bizarre, intricate things to explain the fact that elephants have a long trunk, or giraffes have a long neck, or leopards have their spots. And a real-life example of this, back in 2007, blobology was very popular in brain imaging work. And a bunch of scientists did a study where they took, 10 men and 10 women, put them in the scanner, showed them images of the then presidential candidate, and these were 20 people that were undecided, and then they checked to see what signal was coming through. And they said about Mitt Romney that his they showed videos of still photos. His still photos prompted a significant amount of activity in the amygdala, indicating voter anxiety. And Martha Farah, University of Pennsylvania, said, not so fast, you guys. The Romney, she wrote this in a blog post that I've referenced down there. The Romney amygdala activation might indicate anxiety or any of a number of other feelings that are associated with the amygdala. Why anxiety? Anger, happiness, or even sexual excitement. And I think this was a great way of making the point that you can't do this without a control. You can't just find any kind of story you want and make it just so, and without science behind it. Okay, another example of this is what I call jarking, justifying after results are known. But darling, I was only flirting with conventional levels of significance. Okay, so figure out how to do this. All right. So we've got some interesting things going on here. I love this. So a statistician, Matt Hankins, as part of his blog, went through and decided to document all the ways that people justified why they were talking about their results, even though they weren't significant. So they got a p-value higher than 0.05. Instead of just writing it up and just saying non-significant and being honest, they tried to make it seem like it's something, and they just couldn't call it not significant. So I encourage you to look through this. I love this. Almost marginally significant, approaching our preset significance level, approximating significance, arguably significant, barely significant, below but verging on the statistical significant level. I just love this. Fell only short of significance. It goes on and on and on. I don't know if he's still collecting these, but vaguely significant. I love these. They're hilarious. So if these were results that did not fit in with something that you believe to be true, then you wouldn't even, you would just say, okay, not significant, we're done. But no, somewhere in your gut, you feel like it must be this. So you're only highlighting those with this, well nigh significant, these labels for the things that you really want to believe are significant. And you can't really have it both ways. It doesn't work that way. Okay. Fixes. Let's get on to the fun stuff. Fixes. The first one, a team of rivals. Invite your academic adversaries to collaborate with you on a study. So adversarial collaboration is really an interesting idea. Daniel Kahneman is a big fan of it. And the idea is that you team up with your adversary. Maybe you have a referee or something that's kind of helping. The idea is to disagree as little as possible. So either have two different data analyses, or you go back and forth on the data analysis until you can agree on the method, and then you can write your paper as two voices. So you can say, okay, this team interpreted the data to mean this, and this team, we interpreted the data to mean this, and it makes for a very interesting reading of the paper. Not for the faint of heart, because you really are working with your adversaries, and you have to be really open to their critiques and their criticism. But he felt that it was a much more productive way to find the areas that you really agree on and really disagree on, rather than, okay, publishing something and then someone publishes a letter and then you have the rejoinders and back and forth. He said, shortcut all that. Do it in the study. So if you don't quite have the heart for that, you can become your own adversary. Do those sanity checks on your data. Make sure that things change the way you expect them to change. You can go back and peek under the hood, do some exploratory data analysis, lots of plots, and that's where you can see if you have a problem or miscoded something, or if there are weird outliers that are throwing things off. Dynamic reports like Sweeve and Knitter, you probably know about these, are wonderful because they're highly reproducible. So you can share them around and even share them with your adversaries if you want, and everything is there, very reproducible. All right, devil's advocacy, finding competing hypotheses. So we talked about what happens when you just get kind of myopic on looking at one hypothesis. So the idea here is to specifically develop alternative hypotheses and then test them out. Try to design an experiment that will give you different results, like clearly different results depending on which hypothesis is true. Mostly, we just kind of have one hypothesis and we design an experiment to say yes or no on this. But the really good ones will design an experiment and say, okay, there are these two ideas, and I've designed such a clever experiment that it will look like this to support this one, or it will look like something very different. Bayes factors, likelihood ratio tests are slightly more statistical and very exciting, and I think a good place for the future of science to go. You can explore some ideas behind that with this Shiny Apps link that I've given you there. Again, I don't have time, but it has this great cartoon down at the bottom that explains a little bit of the ideas of what's going on with the Shiny App, and that's by Wagenmakers out in the Netherlands. Some really good stuff there. Pre-commitment. Publicly declare a data collection and analysis plan before you start the study. You swear, and then you stick to your plan. There's a lot of exciting ideas around this. Pre-registration, I think, is one of the big ones. So we know registered report. Sorry. So pre-registration, you're just putting your plan, up online and making it publicly available as a way of just kind of, holding yourself accountable. The next stage for that is a special kind of publication called registered reports, where before you even touch your data, before you collect your data, you write up your protocol, including exactly how you plan to collect your data, when you're stopping, your data collection, how you're analyzing it, everything, then you submit that for peer review. And the reviewers analyze your protocol, your plan, and um, if they approve that, then it's an in-principle um, uh, um, admission, acceptance, sorry, an in-principle acceptance of your paper, no matter what your results are. So this is really nice. It helps you get your publication, um, no matter if you have negative results, but it's also good because you've sworn to something and you have to stick to it, and you can't use those researcher degrees of freedom to p-hack your way into something. Part of what you can do for that, or just separate two-stage analysis, you do exploratory and confirmatory first. So your exploratory results should be labeled as completely exploratory. It looks interesting, it looks intriguing, but this came from us just playing around, and so it needs to be treated with a little bit of suspicion, and we need to do a follow-up study that's designed to specifically test the hypotheses or the results that we got from here. That's separate from confirmatory, which is that second part. Okay, we found these things before, now we're going to test them out with an entirely new study. So you can do cross-fold validation, holding some of your data for training and a testing set. Those are different ways of getting to this idea that you're not overfitting, that you're not just zeroing in on things that are not real. And of course, you should open everything up and post it on something like Open Science Framework, where everyone can see your data and your plan and your code and all of that. Blind data analysis, one of my favorites. Analyze data that look real but are not exactly what you collected, then lift the blind. So Saul Perlmutter talked about how this is standard in some parts of astrophysics because data are so expensive to collect, and they have to do so much pre-processing of the data that they didn't trust themselves not to just be nudging it in the ways that they wanted. So it's standard now where they jitter it a little bit. They jitter the data, add some random noise, permute the label, scramble some variables, keeping track of what they did. But then the person who's doing the analysis works with the scrambled data, the simulate, not quite real data, and does all the pre-processing and all the rules and everything like that until everyone's satisfied, and then they lift the blind. They take all the process they did to that and then apply it to the real data set. And he said it actually brings back a lot more suspense. And he talked about a graduate student of his, and it was for her PhD thesis. And she said it was the end of a long day, a long meeting, and it was a bunch of people, Friday afternoon. And she said, well, if we all agree, I think we're ready to lift the blind. I've done everything, it's good. And he said, everyone was like tired, but there was no way that they wanted to find out the answer. They said, oh no, we're going to stay late for this, and it was just this thing where she said she was able to lift the blind. They had it all automated. And so it's this big suspense, and then it came out exactly the way they wanted, and it was great for her, her results and her thesis, and everyone applauded. And I just love that story because I don't think that we have that often in science right now. You'll get some preliminary results, and then you'll, go to your PI or whatever, and she'll say, well, did you look at this? And you're meandering, and before you know it, you're just nothing is a surprise, and you also can't really trust that you didn't nudge things. Saul said that it was great because he felt free to experiment because he knew that he was protected against his own biases getting in there. So I think this is a really nifty idea. I just wanted to highlight one article that might be interesting for you to look at, where they kind of did everything on this. They were studying a particular principle in psychology from 1968, trying to replicate this. So they did 4 specific tests with competing hypotheses. They used Bayes factors, which I love. So they're considering their alternatives. They have these competing hypotheses. They did it as a registered report where it was all approved ahead of time. They blinded the data, where they randomly permuted one of the variables. Um, the analyst only worked on the blinded data. So once he had the code set, he locked it and posted it on the Open Science Framework, so it was open, and then the code was applied to the unblinded data for the confirmatory results. Then after that, now that it was open, then they did the exploratory analysis of this real data to see what they had. And they wrote them up separate, I mean, the same paper, but confirmatory and exploratory. And they looked at different theoretical explanations for these conflicting results, things that didn't seem right or that they weren't sure. They came up with more than one explanation. So I encourage you to look that up. I think that it's a great example of what you can do. So just some quick recap. You are trying to fool yourself during data analysis. It's not just everyone else, and it's because you're human. We all fall for confirmation bias, so it's good to consider alternatives. How likely are they? Put all this in your paper. And we are all that Texas sharpshooter, so you just have to be alert for it. You find ways to kind of separate the confirmatory from the exploratory, pre-register your study, whatever you need to do, and watch out because we only catch the errors that we're looking for, so you have to be the devil's advocate or find a devil to team up with. So thank you very much. Feel free to email me with any questions or tweet. Thank you. Hi again. Thank you.